Quick side note, make sure human interference is whenever either humans mess up stuff by affecting the environment, the ecosystem, by way of pollution, deforestation, or whatever way they can find. Bye.
Hi, I'm Blake Risco, and this is part of my project on ocean acidification. To start off, it first off begins with pollution and what's in the air, and it starts off with carbon dioxide and the amount of fossil fuels that are burned, causing carbon dioxide, henceforth fossil fuels and pollution. And I have a graph from the USCB Organization on Health and Pollution in the Environment. And so on the left it has millions of metric tons of carbon, so 1,000 million tons, so basically 1 billion tons. It's not good. And we have a whole bunch of years on the bottom. This is kind of a graph of how it's gone over the years. It's kind of hard to see, but it started off in the 1900s. There wasn't really much because there wasn't really much kind of going on at the time. Like cars were like very, very beginning cars and a whole bunch of very, very basic things. And as you can see, it started to come up all across the world. And as humanity started to become more and more reliant on the fossil fuels, you can see the amount of carbon that is released in the environment goes skyrockets all the way up. From the 1960s comes way up to 2000. That's almost a 10,000 increase, a 10,000 million metric tons increase. And it didn't go all the way to 2020 and what it is now, but it probably dropped because of the coronavirus dropping, dropping in people using their cars and the environment. But out of this carbon, 60% of it goes into the environment, as in clouds, as in new civilizations, as in like plants, trees, everything out there. But around 30 to 40% of it goes into the ocean. And out of this ocean, it can really damage what goes on inside of ocean ecosystems and how it develops ocean acidification and increasing pH levels. And I'll talk about that next.
Alright. So what I was saying last time wasn't that the 1900s were the Stone Age, just that they were really earlier in development of huge factories and huge things regarding pollution. Because the Civil War happened 10 years earlier, so it's kind of just saying that it started out pretty small in pollution-wise, and that we weren't coming from a huge pollution. And to start it off, so whenever the carbon in the air goes into the water, it makes it more acidic on a scale, and it's measured on a pH scale.
So, minor mishap on my part. Accidentally, it's from 14 on the pH scale, from 14 to 0, and 7 is the level of water.
And
Whoops.
This measures from 12 to 0. A normal glass of water, or 0 being really acidic and 12 being none at all, extremely pure. A normal glass of water is 8. And the ocean water also started out at 8, but as over the years have progressed, it's logarithmic, so it basically becomes times 10. So one level is basically 10 times worse. We're in the lower 7s, so that's 10 times 10, so it's 100 times worse than what it was. And people really should care about this because it's hurting food webs and ecosystems. And how it's doing that is the carbon in the air affects how much animals' calcium gets. And how that works is the calcium like in your bones and basically like the bone marrow. And this calcium in your bones makes your muscles strong and your bones stronger. And ocean animals have their own version of this called calcium carbonate, which builds up their shells, which builds up like clam shells, oyster shells, urchins. And what it does is this hydrogen from this carbon and hydrogen mix with the water and creates this carbonic acid, which really doesn't sound that good. And so it keeps on taking away this calcium carbonate. And so the animals don't have as much calcium carbonate as what they should. And so it harms them and makes their shells less dense and less strong. And it can also not help animals, as in fish and octopus, because these animals rely on it so heavily that it can deter them from knowing where predators are around them. And it can really and severely affect ecosystems, and we need these ecosystems to survive in order for us to survive, because we eat fish. Me personally, I eat fish almost 3 times a week, and just for the oceans in general, we need all of these animals to provide food for bigger animals. Like, these animals eat off this algae, or not algae more or less, but seaweed. Seaweed needs this needs this calcium carbonate, and the krill need the calcium carbonate for shells. Clams need the calcium carbonate. All of these animals are so dependent, and if it's just gone, then we're gonna lose it forever. And it's kind of hard to find a solution, but in my next time, I'll talk about what my solutions are.
Time for a little break on to show you what the scale looks like for the pH scale and show you how it's represented with seawater and blood.
So basically, here's the actual physical scale. So it starts from liquid drain cleaner and bleaches and ammonia solutions and baking soda and seawater. This is what it used to be. This is from an older version of it. So from what I talked about earlier and how it drops. And the human blood is 7.4. And it's somewhere in the actual ocean water now is somewhere between these. And between blood and the milk and urine, which is really uncomfortable. So, just to have a representation of what it's really like on the scale and what the scale looks like.
What's gone now are the solutions. What people have been trying to do forever is to try to go green. I mean, hey, you've heard of people going green. You see it on the side of trucks. But how many people do you really know that go green? Not many, huh? Our reliance on fossil fuels are so heavy that we are unwilling to change by human matter and by the ocean. It takes usually 10,000 years for any sort of shift in the acidity levels, and we changed it in our entire lifespan of what? 2,000 years? Not even 2,000. How about 100? Going from the 1900s to what it is now. It dropped almost 100 times what it was before. And our reliance is so heavy that it seems almost unfaltering. But one major way we can make a big change is through a new solution that's been found, is being able to produce and plant more and more sea life underwater. Because, I mean, like, if there's more and more seaweed and more plants to absorb the carbon, then there's less carbon intake into the smaller parts of the food web. Like, as I said earlier, the mollusk clams and the urchins that are losing their shells and hurting. And instead of having them to take the blame and take all the brunt force, you can put it more on the seaweed that can just absorb it, and if they die, they die. Whatever. They're seaweed. And so, they're not really the huge pivotal parts like these mollusk clams and other ones are. So, if we can continue to plant more underwater sea life, then maybe, just maybe, we can slow and stop the curve. So, I'm sorry you had to listen to me talk for 7 minutes and 50 seconds exactly. So, have a good rest of class, and good night.